In the 1990s, the COBE satellite made the first maps of the cosmic microwave background fluctuations. In the 2000s, the WMAP satellite made far more accurate measurements of it. And then in the 2010s, the European Space Agency's Planck satellite made this definitive map that I've shown you, which really gives extremely high precision measurement of this. And from this, we can measure, for example, the curvature of the universe. We can measure the density of the dark matter. We can measure the density of the baryons, the hydrogen and helium. We can measure the neutrino density. We can measure all of these things to sub-percent precision. So this is super high precision measurements of things like the densities of different materials in the universe. It's an incredible data set. And ironically enough, this picture of the universe with us at the center and the cosmic microwave background and finally the outer sphere of the Big Bang around it is remarkably reminiscent of Ptolemy's cosmology, right? Except that this now obeys the cosmological principle in the sense that everyone in this infinite universe sees exactly the same thing. There's still no special position, but we look like we're special because of this effect of looking out in space being looking back in time. So instead of the Empyrean realm or the sphere of the fixed stars at the edge of the cosmos, instead what we have at the edge of our cosmos is the Big Bang, and beyond that there's nothing at all because the universe had not existed before that. So this is what we see. This brings up some puzzles, in particular this incredible homogeneity of the cosmic microwave background. Remember that the observable universe is small early on and gets bigger later. So if the universe is 1 million years old, the observable universe is only about 1 million light years in radius. Actually, expansion effect's about double that. It's about 2 million light years. And so you can't see, and then when the universe is 10,000 years old, the radius of the observable universe is only about 10,000 light years. So if you look at the cosmic microwave background and say, okay, if I look at a point here, this photon is coming to me. When that photon was emitted, the observable universe at the time that photon that I'm observing here was emitted into space, the observable universe was only a few 100,000 light years in diameter. So this photon's observable universe, when it was emitted, is only about that big, and on the sky today, it's only about 1 degree, about twice the size of the full moon. This photon over here, his observable universe would have been that big, and so on. And you can kind of see this actually. You can kind of see that the characteristic size of these blobs is about all the same. That's because the blobs couldn't get any bigger than the size of the observable universe, right? And so now we have a real puzzle because this spot here and this spot here and this spot here, all of these spots are the same temperature, 1 part in 100,000, yet there's absolutely no way for them to have communicated with each other since the moment of the Big Bang, because there hasn't been enough time for light to get from here to here. So this and this and this and this are effectively completely separate universes. They were never in causal contact with each other, yet somehow they managed to reach equilibrium in temperature to an incredible, sub-percent level. And the standard Big Bang cosmology doesn't explain this, right? You basically have to assume it is a boundary condition. You just say, well, the universe started out highly homogeneous, but there's no particular reason to expect it. I mean, it's just like kind of, well, God did it, So the standard cosmology, this picture of the universe filled with matter, radiation, and vacuum that started out in an infinitely dense, infinitely hot, coming out of a singularity, the standard, what's called a lambda cold dark matter cosmology, it fails to explain a lot of the basic properties of the universe, why it's so big, why the universe is so old, right? Why is the universe, if you just plug in Einstein's theory of gravity and look at the natural sort of how old what the lifetime you would expect the universe to be, you would expect it to only live for about 10 to the minus 35 seconds, but it's lived for 10 to the 10th years, right? Why? So why is the universe so big? Why is it so old? The characteristic scales are the scales associated with gravity. You would expect the universe would just be this tiny little thing that would recollapse on itself, and that would be it. Of course, we wouldn't be here to observe it. Why the universe is so homogeneous, right? How did the cosmic microwave background get into perfect thermal equilibrium to 1 part in 100,000 when all of these spots were essentially separate universes who had never communicated with each other, right? And also, why is the universe so close to geometrically flat? You can measure the curvature of the space, right? So there are 3 possibilities depending on the density of the universe. Either you're positively curved, which means that the universe is the surface of a sphere. This is a little hard to imagine because in this picture, it's the 3-dimensional surface of a sphere in 4 dimensions. So it's without a boundary. We just live on the surface, right? but it's closed on itself. Or the universe is the opposite, which is called a negatively curved space, or it's exactly on the boundary between the two, which says that the geometry is flat. And observations, in particular observations of the cosmic microwave background, tell us that the universe is exactly geometrically flat to within we've measured it to within less than 1%, right? But in fact, the lambda CDM cosmology doesn't explain the flatness of the universe either. All of these basic properties of the cosmos that we observe it to have no essential cause in this picture of the universe. So this picture of the cosmology, as successful as it is, we can work this forward. We can understand how galaxies form. We know the initial conditions. We can see it all. We can just look at it with telescopes. Very successful. The theory matches the data beautifully. There are a couple of mismatches here and there. There are things we're still working out, but it's a very successful theory. But none of its basic properties are explained by the theory itself. So this picture we have of the universe we know it's incomplete because it doesn't explain most of these properties. And furthermore, the standard model of cosmology doesn't explain these little fluctuations either. Not only does it not explain why the cosmic microwave background is so homogeneous, it doesn't explain why these 1 part in 100,000 fluctuations have the properties that they do. And so we also want a theory that says, where did these initial perturbations come from that later collapse to form galaxies and clusters of galaxies and so on? So these are also a mystery in this picture of the Big Bang that I've been telling you about. So we need a better theory. We need a deeper theory in order to understand these kind of existential questions about the universe. Why is it so big? Why is it so old? Why is it so homogeneous? Where did the inhomogeneities come from? And why do they have the particular form that they do? Why is the universe geometrically flat? This brings us to a more modern theory called inflation, which has its origins. It was the first paper that completely proposed an idea of inflation was by Alan Guth in the early 1980s. Earlier papers had been floating around that had gotten most of the way there, but hadn't quite put it all together. And it was Guth that really put it together finally. And the idea of inflation is that this is a period of expansion that happened before the onset of the hot Big Bang. So we now have this picture. If we go back in time and the universe would have been denser and denser and hotter, going all the way back to this initial singularity. Inflationary theory takes away that initial singularity at the Big Bang and instead tacks on before that. It says what happened before the Big Bang. So instead of having a singularity, what you have is the end of this inflationary period. So this is really a theory of what happened before the Big Bang. And this theory of what happened before the Big Bang is very different. The universe was not hot. It was cold. It was almost at absolute zero. And it was completely empty, full of nothing but the energy density of empty space. So the inflationary picture, what happened before the Big Bang was a universe that had nothing in it but vacuum. And it turns out that if you have a universe with nothing in it but the energy of vacuum, it expands exponentially quickly. And this energy of the vacuum during inflation would have been huge. It would have been an enormous energy density, which meant that the universe would have expanded enormously quickly. And so it would double and double again and double again and double again in size, and it would double again more than 120 times at least, right? So you have this enormous, incredibly rapid expansion of the universe that happened before the onset of the hot Big Bang. And the hot Big Bang happened when this vacuum energy decayed into all the particles of the standard model. And we'll talk in a minute about the mechanism for that. And this, it turns out, sets up the initial conditions, and it sets up these boundary conditions. For example, it creates a flat, homogeneous equilibrium universe in a very natural way. And we'll talk about how that happens. But the basic idea is you're replacing that Big Bang with an earlier period of vacuum-dominated expansion. The universe was absolute zero, filled with nothing, completely empty, filled with nothing but empty space. So how can nothing be something, right? How do we do this? And in particular, this is funny because this period of vacuum-dominated expansion has to end somehow. It has to transition into this hot Big Bang. So it has to be dynamical in some way. This energy, this vacuum energy can't just be static. It has to have some kind of dynamics to it. And so in order to understand that, in order to come up with a theory of it, we're going to steal something from particle physics. And this is where people trained in particle physics like me come into this picture. And what we're going to steal from particle physics is the idea of symmetry breaking. And this is ubiquitous, for example, in the standard model of particle physics. It shows up in condensed matter physics a lot. But in order to understand symmetry breaking, I want you to imagine a pencil balanced on its tip. Okay. So now this is unstable, right? You balance a pencil on its tip, what happens? Falls over, right? You know, little air currents or even quantum mechanical fluctuations will push that thing off and it'll fall over. It's in unstable equilibrium. But it's symmetric, right? So in particular, it has a symmetry in that when the pencil is standing up on its end, if you rotate that pencil about the vertical, you get the same thing back, right? It's symmetric under these vertical rotations. But when the pencil falls over, because this is dynamically unstable, right? So that if I let the pencil drop, it can drop in any direction it wants. There's no preference, right? Because this is a symmetric state, it's equally likely to drop this way or that way or that way or whatever. There's no particular preference for how it drops, but whichever way it drops, it picks out a direction. So now the pencil lying on its side is no longer symmetric under that rotation about the vertical, or the symmetry is called broken. So this dynamically, we have an unstable state that is symmetric, and we have a stable state that breaks the symmetry, that no longer realizes this rotational symmetry about the vertical. This is a very common process in nature. You have systems that are symmetric but unstable, but the stable state actually fails to realize the symmetry in much the same way that the rotation of the pencil does. And so this pencil now also, when it's on the vertical, it has potential energy, right? And so as it drops, its potential energy into the gravitational field drops as it drops. So we can make a plot of the potential energy of the pencil as a function of its angle of tip. And so the energy is high when it's on its tip, and it's at a minimum when it's on its side. But since it doesn't depend on the direction, it makes this sort of circular thing. It looks like a sombrero, right? This is what particle physicists call this a Mexican hat potential, right? So and now the physics of this, you can think of it as like a ball rolling down a hill. This pencil tipping means that the angle of tip gets bigger and bigger, and when it's down here, you're at the stable state. So we can plot the energy of this system as like a ball rolling off the top of a hill. This is unstable up here. The ball wants to roll down and live in this trough on the bottom. Okay. When the ball's up here, it's symmetric, right? You can rotate about this and the state doesn't change. When the ball's down here, it's picked out a particular direction in this trough and the symmetry is broken. This is exactly what happens, for example, with the Higgs boson in the standard model of particle physics, where this symmetric state is a state in which all the particles in the standard model are massless. When the Higgs boson symmetry is broken, and now this symmetry is in this abstract group space, but it's pretty much the same thing as a pencil falling over. When the symmetry is broken, all the standard model particles acquire mass, and the Higgs boson itself is massive. So in order to think of this, for example, in the Higgs field now, it's not like one pencil balanced on its tip, but you have to imagine that all of space is filled with pencils balanced on their tips, one pencil at every single point in space, an infinite number of them. And then when the symmetry breaks, all those pencils fall over in the same direction and pick out a direction, a broken symmetry in that space. So the Higgs boson, for example, is an example of a field, so that when it's in its symmetric state, it has potential energy. The vacuum has energy that is the potential energy of this field that permeates the entire universe. When the symmetry breaks, when the pencil falls over on its edge, that symmetry is broken, and all the particles acquire mass by their interaction with this field that permeates the universe. So this is how the Higgs field works in the standard model. We also borrow this for inflation. In particular, then, what we have is in the early universe, we say that during inflation, this thing would have been sitting up on its peak. The universe would have been full of vacuum energy, but would have driven this incredibly rapid expansion. And then at some later time, this field, it's unstable, so eventually it drops off the peak. It goes down here, and this energy that it had while it was up here gets transferred into, decays into all the particles of the standard model, heats the universe up to a super high temperature, and we end up with this homogeneous hot initial state of the Big Bang that comes from the decay of this energy that was associated with this vacuum field. This is the idea of inflation. You start out with an unstable vacuum, it drives exponential expansion, and then eventually that vacuum decays, and that energy gets turned into all the particles that fill our universe today. All the hydrogen and helium and dark matter and quarks and electrons and positrons all come from the decay of this vacuum energy that filled the zero temperature universe before the Big Bang.